We're starting with a lot of information on the board today. That's because we're picking up kind of in the middle of an example from last time. So these are mostly reminders of what we were doing last time. So last time, the big thing we decided to do is we decided to skip solving the differential equation. Right? In the past, when we did particle in a box, harmonic oscillator, rigid rotor, even a hydrogen atom, we actually solved the differential equation or borrowed somebody else's solutions. And we said, okay, but if we've got that electron-electron repulsion term, we're not actually going to be able to solve the differential equation, so we're just going to make a guess. And we talked a bit about what makes good guesses: physical reality, variable, a parameter that can be changed, easy mathematics, things like that. And we said we're going to use this for the variational method. We're going to minimize the energy of a guess function, and that will always be greater than or equal to the ground state energy. So we're looking at this to find an approximation of the ground state energy. And this is the equation we're using where phi is our guess function. So we're saying phi is our guess function. And last time we said we're going to do this problem where we say, okay, let's pretend we can't solve the Schrodinger equation. And let's say we're just going to do the Schrodinger equation. We don't want to solve that three-dimensional differential equation with the sine theta, d theta, all that stuff. We don't know where the Laguerre and Legendre polynomials come from. We want some other way to approximate the ground state energy. And already you can get a sense of there's going to be restrictions on the usefulness of this because we're getting ground state energy. Like I said, there's some tricks where we can get higher excited states, but what we're looking at is just getting ground state energy. The good news is I found my math mistake, and it's a rather simple little one where I was like, I feel like I'm off by a factor of 2. It was a silly little mistake. But just to redefine the problem real quick, our Hamiltonian is going to be negative h bar squared over 2m del squared minus, we set z equals 1 because we're doing hydrogen, so it's e squared over 4 pi epsilon naught 1 over r. With our guess wave function, we decided we were going to guess something that was like e to the minus ax squared. And we solved, last time we solved this bottom part, and that's where I was off by a mysterious factor of 2, which I have since discovered. It's really simple. We end up with an integral that's essentially, we get the triple integral, where we're doing dr, d theta, well, let's do this the way we typically do it. We are doing e to the minus 2ar squared, r squared sine theta, dr, d theta, d phi. R is 0 to infinity, theta is 0 to pi, phi is 0 to 2 pi. And we said the sine theta, d theta, d phi part, that's pretty easy to do. That gets us a factor of 4 pi. The place where I missed my factor of 2, I was going off of this equation, which I think is off the screen for the even integral of a Gaussian function. And notice this a here has no 2 out front. And when I was copying it down, I just forgot that this is a 2a. So that's where my missing factor of 2. I copied down that equation, forgetting that I had 2a. So when we solve this, and I encouraged you all to find my typo, so hopefully you all went and tracked it down. We got 4 pi times, I'm going to plug everything into what's up there. This would be for n is equal to 1 in this case, so I'd have 1 over 2 squared, and then 2a to the 1 pi over 2a to the 1/2. Again, because I've got 2a up there. Of course. But, you know, when it's the last part of class and you're trying to get through all your notes, sometimes you... So that's where my missing factor of 2 came from. We can simplify this, and we just get a simple pi over 2a to the 3 halves, if we simplify that down. Now, the part that we started getting, the other part we started on just at the end of class last time was this top part, doing, this is bottom parts here. That top part is a little bit more complicated. And, you know, it's always more complicated when we're doing the top part because we're going to have the Hamiltonian, right? The bottom part is essentially just doing normalization. Essentially, what we've calculated here is a normalization constant where a is our parameter to vary. It's our variational parameter. So our normalization constant has this parameter to vary, but we still have to solve that top part with the Hamiltonian. Notice this is still different than solving the differential equation. When we solved the differential equation, we were essentially doing the same thing where we were trying different functions and seeing what worked. And now what we're doing is we say, look, okay, we know this function isn't going to work, but it's going to be pretty close. So now we just have to do this integral. I'm going to break it up into 2 parts. And we're going to start by, it's actually going to break up into multiple parts, but the first thing I want to do is I just want to do the Hamiltonian operating on e to the minus ar squared, e to the negative ar squared. This is going to give, so I'm just doing this part first, Hamiltonian operation. And then it's just going to be an integral of some functions. So I'm going to go ahead and operate my Hamiltonian on that. That's going to be a negative h bar squared over 2m del squared on e to the minus ar squared minus e squared over 4 pi epsilon naught 1 over r e to the minus ar squared. That attractive term is pretty easy to take care of. It's already done. We just have to integrate that. This is the part that's a little bit more tricky. We have to remember that this del squared is in 3-dimensional space, so it's a 1 over r squared d by dr, r squared d by dr on this. And we did go through that last time, which is why I'm not doing it again right now. And this was another thing where I was like, between now and the next class, go and do this. So hopefully you went and did this, and you were able to prove to yourself that you are going to get 4a squared r squared minus 6a e to the minus ar squared. And that's just the Hamiltonian operating on this part. I still have to multiply by my phi star to get the thing that I'm actually going to integrate. So you all did this at home, right? Question?
I did a question like that, but they don't use like that information. They use the kinetic and the potential. So instead of they set a Hamiltonian to the t plus b, then they solve for the 1/2 kx squared plus the.
So if they're doing 1/2 kx squared, that's for the harmonic oscillator. So that's doing a similar but different problem. And we can see we're doing the hydrogen atom, so we've got our kinetic and our potential still, right? So it's still closely related, same type of idea. We've got our kinetic, we've got our potential. I'm going to just go substitute this in, and you can hopefully already see the train coming a little bit. We're going to end up with several easy integrals. And what I mean is we're going to have an integral that's going to have like an r squared times, an r squared times, so we're going to have an e to the ar squared r to the 4th. We're going to have an e to the ar squared term, and we're going to have an e to the ar squared r term. So we're going to have 3 integrals. All are going to fit into one of these 2 Gaussian integral definitions. Let's see, where best to do that. I want to leave that list up. I'm going to just go and do it here. So we're going to take this stuff in green, that's going to be this top part, is going to give us 3 integrals to solve. I want to leave that list since that's kind of the whole point of what we're doing today. And So if we're looking at the integral of phi star h hat phi d tau, we're going to get 4 pi from doing the angular parts times negative h bar squared on 2m integral 4a r cubed, oh, well, not cubed, oh, r to the 4th e to the minus 2 ar squared dr. So I did a couple things there. Thing number one is I combined this r squared with the r squared from our volume element. That's why I got an r to the 4th. And then I combined my e to the ar from the first phi with the e to the ar in the second phi, so I get another e to the 2ar. So I just combined things. It's going to be plus the second integral, which is going to be 4 pi times negative h bar squared over 2m integral. I should bring this negative out front. Negative. So I'm bringing the negative out front. 6a e to the minus 2 ar squared. Oop. This time I forgot to bring it out front, but that's okay because it's only the r squared dr. That r squared I should have put out front just to be consistent. Again, that's from the volume element during the triple integral. So that's that term. And then I'm also going to have a minus 4 pi e squared over 4 pi epsilon naught integral r e to the minus 2ar squared dr. These are the three integrals. I've got 2 from the del squared term, 1, 2, and then a third from that one. So these are the three integrals that we need to solve at this point. We're just doing using definitions of integrals. Question?
You said it was initially addition for the second integral?
Oh yeah, that's because it's negative 6a.
Okay.
So I was about to write it like this, with the negative, with a plus and the negative in there, but that looked funny to me.
I mean, but there's also the negative in the h bar.
Oh yeah. I could just cancel the negative in the h bar. That also works. And then I could just leave that plus. Either way, right? I have a couple that I have a tendency to leave extra negative signs so I don't accidentally cancel things. But yeah, I could have just canceled the negative in the h bar. I just wanted to make sure I didn't forget the negative for that part, because that would have thrown us off dramatically.
Did the 4 pi like part come from
So-
the volume element?
Yeah, so the 4 pi came from the volume element doing the sine theta d phi. That's where the 4 pi came from. And since our guess function didn't depend at all on theta or phi, seemed like okay. So at this point, we are just using the definitions. And I'm just going to kind of circle the part that's what we're going to use the definition for. These are all 0 to infinity, 0 to infinity, 0 to infinity. So we can use our Gaussian function definitions. This one is going to go to a 3 over 2 cubed 2a squared times pi divided by 2a, the 1/2. Very similar to the last one we did, the one we did in blue, except for now our n value is 2, so I get 2 cubed 2a squared on bottom. This one is also going to use the same even type idea. This one is just going to be 1 over 2 squared, 2a to the 1, pi over 2a to the 1/2. Using the same definition that we used last time, both of those Gaussian integrals were for even r values, so they use the same definitions. This last one uses the odd definition, which is actually almost a little bit easier. This part, sorry, I should circle the integral in there as well, because this is doing the integral. 1 over 2, 1 over 2a. Right, so in this case, my n value for this integral would be 0. I'm going to have n factorial, 0 factorial is 1, divided by 2, and then a to the 1. Or in this case, again, I've got 2a in my integral, so I get a 1 over 2a. Okay, now that's the hard part, essentially. Now it's just algebraic manipulation, right? You're gonna multiply through, collect terms, cancel terms, all of that. And if you do all of that, you'll get something that looks like this. Giving both the top part and the bottom part, you've got that 4 pi out front. You're going to have h bar squared over 2m times 3/8 pi over 2a to the 1/2. It turns out all of these other like 2a terms end up canceling out. Sorry, I forgot to square there. That's important. A squared in that top term. That first integral should be an a squared. The reason that's really important, and that was just me forgetting to write it down from the other part. The reason that's really important is because it's going to cancel with this 2a squared and make our lives a lot easier. Same thing is going to happen here. That a is going to cancel with that a, and that's going to make our lives a lot simpler. So it turns out that for these integrals, it's all going to be in terms of this pi over 2a term with the extra fraction. So you get 3/8 pi over 2a. That takes care of the first two. And then you're going to have a minus e squared over 4 pi epsilon naught 1 over 4a. So this top part in green, that is essentially the integral we just solved with our collected terms. And yes, I could cancel out the 4 pi, but again, I'm just keeping everything, and we'll simplify it more in a minute. The bottom part, that's the divided, that's what we got earlier. That's the pi over 2a to the 3/2. Oh boy. Okay, why did we just do all of this? Right? So we got to remember, the whole reason we're doing this is so we can skip solving the differential equation, or so we can, for two reasons. One, because we don't want to solve the differential equation, or two, because we actually can't solve the differential equation. Pretty much every problem we look at from here on out, we can't solve the differential equation. So we made a guess. We solved our integrals. This is the solve. And now what we have to do is we have to minimize this energy with respect to the parameter. So essentially what we'll do is we'll say we want to find an energy minimum. And right now it's a little bit messy, but we'll, again, algebra, and you can start doing the algebra now on your own if you want to simplify this. But we're essentially going to do we're going to take the derivative of that energy with respect to A. And then we're going to solve for whatever A value we end up with. This is going to give us our minimized energy. Possible we get a maximum. That's why we have to be careful about making sure we have good guess functions. This will result in just, we have to be careful making good choices, but this will, if we solve correctly and pay attention, this will give us a minimum. So this is going to give us a way to find that approximate ground state energy. To make it easier, we can do some rearrangements here, right? I can bring, notice I've got a 2a to the 1/2, 2a to the 1/2. I can cancel those out. I've got a 4a. I can turn that into a 2a to the 1/2 times another square root of a. I can cancel that out. I've got pi's all over the place. I can cancel those out. There's a lot of simplifications we can do. And if we do those simplifications, this energy term can actually just be written as 3h bar squared over 2ma minus e squared over 2 pi. Let's do it this way. Trying to figure out the nicest way to write it down. Okay, we'll do it this way. 2 pi cubed to the 1/2 epsilon naught square root a. And actually, I'm going to read that square root of a as a to the 1/2 because that's prettier for taking the derivative. That's the only reason I'm doing that. So we're taking the derivative, we're finding the minimum energy associated with, or the a that will give us the minimum energy. Yeah?
What is the power on the pi?
That's a cube.
Oh, okay.
I'll make that a little more clear. Is that a little better? Okay, pi cubed. And I was debating whether I wanted to do 2 to the 1/2 pi to the 3/2 to just have that consistency of pi to the 3/2, but I just pi cubed to the 1/2. Same. Okay. Are you all doing the derivative right now? Oh, no? Okay, you can. Okay. This is something you should already be able to do. Right? We're going to get a 3h bar squared over 2m because this first term is just in terms of a. And then we're going to get an e squared 2 pi cubed to the 1/2 epsilon negative 1/2 times a to the negative 1/2. We're going to get an a to the 1/2 on bottom. Right? And if you algebra it correctly, you're going to get a is equal to m squared e to the 4th divided by 18 h bar squared pi cubed epsilon naught squared. Now this is the a that minimizes our energy. So if I want to get my minimized energy, I'll leave that. Oh, I'll do it this way. If I want to get my minimized energy, I'm going to take this a that I just solved for, and I'm going to plug it back in. Right? So I took the derivative to find my minimized energy. Now I'm just going to plug this a term back into my energy expression. See what I get. This will be a minimized energy with only one guessed parameter. There's only one parameter that can vary. But my minimized energy would be 3h bar squared over 2m times my minimized a, m squared e to the 4th over 18 h bar to the 4th pi cubed epsilon naught squared minus e squared over 2 pi cubed to the 1/2 epsilon naught times m squared e to the 4th divided by 18 h bar 4th pi cubed epsilon naught squared all to the 1/2. Right, so I just took that parameter we solved for and plugged it back in. And the reason I wanted to do this is because your textbook never actually does a variational problem where it actually goes through the process of what you do for a variational problem. And essentially, every problem that they solve in Chapter 9 if you're in 10th ed, or no, oh, now I'm getting my chapters confused. Chapter 9 if you're in 11th ed, or Chapter 10 if you're in 10th ed, actually is doing this process. And they're just like, oh yeah, and then you use the variational process and you get an answer. And they never actually show it to you. So I wanted to show it to you at least once. Question?
Should that be an h bar to the 4th or squared?
Which one?
Right, the one on the bottom. Like
That's a 4th.
So the one in the a when you solve for it, that's a squared.
Ooh, did I write down the wrong thing? I wrote down the wrong thing. That's why. This A should be h bar to the fourth. And the reason I know that one's correct, well, there's a couple reasons I know that one's correct, is because I should end up with something that's 1 over h bar squared. And I know that because I already know that. I got the answer written down in my notebook. But this is going to cancel out 2 of those h bars, and then this is going to be h bar to the fourth to the 1/2, so we're going to get a 1 over h bar squared. And the reason that that matters is if we go through and we start simplifying things, notice, let me see, we're going to end up with one mass on top. I'm just going to do a little bit of simplification. I'm going to end up with an m e to the fourth on top. I'm going to end up with an h bar squared on bottom. Let's see, I want to make sure I don't mess this up. We should, pi cubed, 1/2. I'm gonna do something that's a little bit weird, but it's gonna make sense in a moment, I hope. I'm gonna have, I think that's kind of hard to see. Let me do this a little bit differently. I'm gonna write down the exact same thing. I'm just gonna try to write it down so it's a little easier to see. So this will end up, I'm gonna again collect terms. I'm gonna end up with a mass on top. I'm gonna end up with an e to the fourth on top. I'm going to end up with an h bar squared on bottom. I'm going to end up with an epsilon not squared on bottom. I'm going to end up with a pi squared. I'm going to have another one, a factor of a pi out there. But the reason that this is important, let me see, n e to the fourth pi squared epsilon not squared h bar squared. And then this 18 times this 2 to the half. The thing that I'm trying to get at is this collection of constants should look familiar. A little bit. Remember, we're solving the hydrogen atom here. This is actually going to be related to the Rydberg constant. This is the Rydberg constant. So going through this whole process with our silly guess function, we're like, we're not going to solve it. We're going to guess. With a guess that was a reasonable guess, e to the minus a r squared. Going through this process of making a good guess, solving the integrals, minimizing the energy, we actually get the Rydberg constant back out. Something related to Rydberg constant. The actual value we end up getting, there's an 18 times 2, so there's like a factor of 36 there. But the actual value we end up getting is 4/3 1 over pi Rydberg constant. That's what we actually end up getting. This is, I think I called it RH in this class. Sorry, 124 versus 353, RH. So this is actually going to end up being negative 4.4244 Rydberg constant. We get the Rydberg energy back, kind of. Now, if you remember from when we actually solved this for the hydrogen atom, the exact answer was negative 0.5 Rydberg constant. So we've gotten an energy that's higher. We're about 0.08 out of 0.05 off, so we're looking at that's over a 10% error. We've got some error associated with this, but we only used one parameter. And I didn't have to say, oh, let's borrow somebody else's solutions that, we don't know. Just take the Laguerre-Legendre polynomials, I hand you out pages, and say, there are the answers to the differential equation. We're saying, let's not solve the differential equation. Let's guess, And with a relatively simple guess in integrals that are much easier to do than those differential equations, we actually get something that's not that terrible. And now we can start to think, we can do kind of the optional number 4. Option number 4, this optional step, is going to be really important when we go to more complicated functions. But right now, we can look at this and say, okay, with this simple guess function, what could we do to improve this? And there's a couple different ways that, and essentially, a large portion of quantum mechanics, since this came about in the 1930s, has been making better and better guess functions, getting better at guessing good things and finding where those guesses are working better and where they're working worse. And there's some really interesting, it's kind of interesting, so this, quick aside, sorry for this, I'm really interested in some of this stuff, particularly for condensed phase calculations. And with the increased computing power, people have been making worse guesses. Our computational accuracy has been actually getting a little bit worse because people are able to make broader and more absurd guess functions and just let the computer take care of it. So in the increased computational power, it's not true across the board, but for DFT density functional theory, there's evidence that in the last 10, 15 years, the set of guess functions we've been using have been getting less accurate. Now, you could argue that they're just getting more specialized, but it's really the increased computing power has let people just say, we're going to guess like 50 parameters and let the computer put it on a supercomputer and let it solve it, which is great, unless your guess functions aren't well behaved and not, well formulated, and then you just kind of end up going off on a side tangent. So let's talk about some other guess functions we could do, because I have this big note here at the end of it. Not quite right, but close. We could guess anything. Anything. So what are some other things that we could guess? What are some other types of structured problems we could do? And, oh man, I'm so... So one of the common things, like if we wanted to do, where was that note I had? Here we go. If we're looking at, so the case we just did was 1 electron, 1 nucleus. We can guess things that are like the 1s1, which are going to be like e to the minus a r squared. They're going to be related to something like that. Simple guess. If we're doing 2 electrons, 1 nucleus, this would be the helium problem that we originally didn't solve. We can do guess functions that are going to be created from a secular determinant, 1s alpha 1, 1s beta 2, 1s beta 1. Oh, no, beta 2. 1s alpha 2, 1s beta 2. Okay. Which gives us 1s alpha 1, 1s beta 2, minus 1s alpha 2, 1s beta 1, where we can essentially use the same guess function for each of these, saying that this is going to be something like e to the minus ar1 squared, e to the minus ar2 squared. Still one parameter, but now we're essentially parameterizing some other guess function, and we can start building this up to higher and higher complexity. Yeah?
Should there be a 1 on the bottom? With a 1 is there 2 right there in the bottom in the middle?
Oh, yes. Yes. Thank you.
No, it's not.
No,
Wait a second.
it should be
Hold
one
on.
of the betas should be
1s alpha 1, 1s... Oh, here.
Yeah.
There we
beta
go.
1 at the top.
1s alpha 1, 1s alpha 2, 1s beta 1, 1s beta 2. So I get alpha 1 beta, I know this part's right, alpha 1 beta 2 minus alpha 2 beta 1. Okay, sorry about that. Too many 2's and 1's. This is something we should practice. This is something we should make sure we're doing okay with. and I didn't follow my own system for writing it down. I always do the columns all at once. So I do my 1s alpha, 1s alpha, 1s alpha, 1s alpha, 1, 2, 3, 4. Then I go to my next one. And in my rush, I didn't follow my own system for doing that, and I messed myself up. So, but we can essentially say we've got these types of guess functions where we've got two R components, and we can make some guess function for 2 electrons with 1 nucleus. Yeah?
Would the A parameters in the second case be the same for each term, or would they be different?
We could. So you're talking about doing additional parameterization, right? So we could do this with one parameter where it's the same A for all of them, and we're just going to solve for that A. We could also do like an A1, A2 situation where we would end up doing 2 equations, 2 unknowns. That's what we're going to get to next. And then we would also have an alpha 1, beta 2 here at the end. Because the spin part still matters, that's still important. But notice it's not really going to play a role in our integrals. It's just going to ensure that we have that asymmetry. The thing that we are leading to is this idea. 1 electron, 2 nuclei, or 2 electron, 2 nuclei bonding. Yeah?
Is that just for the first term?
That's just for the first term, and then we'd have a second term for the second one.
How come 2 nuclei share 1 electron?
So, bonding. So this is what we're getting towards. This is the idea of we've got 2 nuclei, and the electron is feeling the force from both of them. Right? It's sitting in between them and feeling the force from both of them. And that's going to start the idea of bonding. So the simplest example that we do for bonding is not a real thing. It's H2+. It's the hydrogen molecule ion. And the reason we do that is because doing it for 2 electrons, I'll write this down, and then you see how it gets more complicated for 2 electrons, 2 nuclei, and why we start with this fake simple example to get the mathematics right. So if we're doing 1 electron, this one. If we're doing 1 electron with 2 nuclei, we essentially treat it like sums of wave functions. And we're going to talk a lot about this one in just a second. In this case, C1 and C2 become my parameters that are going to vary. And I'm going to use my actual hydrogen 1s function. Sorry, there's only 1 electron, so that should be 1sa1, 1sb1. I'm going to use my 1s orbital on the first nuclei, nuclei A, or my 1s orbital on the second nuclei, nuclei B. And we'll see how having 2 parameters gives rise to 2 equations, 2 unknowns, and how we can solve that. And that's to lead us to something real. 2 electrons for 2 nuclei. Hydrogen, H2. And in this case, we would end up with a C1, 1s, A1, 1s, B2. So notice 2 electrons, so we're going to have this like 2 electron idea of having a product, but we're also going to have an addition plus C2, 1s, A2, 1s, B1. And then we're also still going to have to take into account the spin part, making sure we've got something that's going to be antisymmetric. Oh. So for just 2 electrons with 2 nuclei, we're actually going to have 4 terms to make sure we have an antisymmetric wave function.
If the 2 nuclei are the same, then are the C1 equal to C2?
I'd like to think so. But now I kind of want to do the calculation to make sure.
What is C1 and C2?
So C1 and C2 are going to be the parameters that we vary.
Oh, okay.
So we're setting up a situation where we've got multiple variational parameters.
Okay.
Rather than having just one where we had our parameter A, lowercase a is our variational parameter. We've now got C1, C2 for our variational parameters.
Okay.
And
Yeah.
that can be any number, they don't have to be quantized.
The variational parameters
Yeah.
do not have to be quantized. They can be any number. You know, just like we saw in this, our A was definitely not quantized. It was some numerical value. Definitely not quantized. So this is, and the reason I wanted to do the variational parameter, the variational method now, even though it's at the end of chapter 9, 10, depending on which textbook you're in, is because throughout section 9a and 9b, it refers to things like Slater-type orbitals and different integrals that you're going to run into, all come from variation of parameters. All of it comes from variation of parameters. But then they're like, don't worry, we'll solve that in 9D. And they constantly, throughout chapter 9, this is in 11th ed, throughout chapter 9, A, B, and C, they constantly are like, don't worry, we'll get to it in 9D. And it's like, why don't we just do 9D first? And then, you know, it's not like, don't worry about it. It's like, oh, we know how to do the mathematics. So pretty much each section of the textbook goes through these different type of guess functions, getting up to this most interesting one that we could then use to develop molecular orbital theory and kind of broaden this to talk about molecules and the electron clouds across many nuclei. Yes?
What's the difference between 1s alpha 1 and 1s?
So 1s alpha 1, 1s alpha 1, 1s beta 1?
A1 from below.
Oh. So 1s alpha 1, alpha is talking about the spin state. 1s A, since this is two nuclei, this is like nuclei A, nuclei B, with an electron being attracted to both. And I'm a little bit torn. I'm going to set up the next problem. I have a worksheet that I want us to do that I think is worth spending time on. But I also forgot we have a Muse Day in week 9. I mentioned that last time. And so I feel like I'm short on lectures. It's stressing me out. So I want to set up this next problem that we're going to look at, which is essentially we're going to look at something like this. That's going to push us towards understanding molecules. We have to start with this fictional case. I know 1 electron for hydrogen is not stable, but it gives us a good starting spot for how we can understand the mathematics and how we can just extrapolate the mathematics for multiple guess functions. So, essentially, we're still doing variation of parameters. We're still doing some E phi is equal to integral phi star h hat phi divided by integral phi star phi, both with d tau. And we can kind of do this without even defining what our Hamiltonian is, and we can do this generically for a generic Hamiltonian. And we can guess our phi is going to be a linear combination of functions, like this. So I'm just going to call it C1 psi 1 plus C2 psi 2. And the question becomes, how does this lead us to something interesting? And so we're going to do the exact same thing we did before, but now we've got 2 parameters, so we're going to end up with 2 equations with 2 unknowns. And we're going to solve top and bottom, except for I'm going to make things a little bit more simple. So if I just plug in this definition of phi, I'm going to have on top C1 phi plus C2, sorry, C1 phi 1 plus C2 phi 2 star h hat C1 phi 1 plus C2 phi 2 d tau divided by integral C1 phi 1 plus C2 phi 2 star C1 phi 1 plus C2 phi 2 d tau. Question?
Should that be phi or psi on each? Because we're defining that phi is C1 psi.
Oh yeah.
But, I mean,
Let's just change
Yeah,
this to phi goes to phi 1 phi 2. because I don't want it to get confused with actual solutions that are wave functions. So I'm going to extrapolate my phi into a C1 phi 1 C1 C2 phi 2. What did I put in my notes? I put size in my notes. Bad note taking. Either way is going to work out fine because we're about to drop that notation as we expand this. So we're going to end up with several integrals. And again, the reason we're setting this up is to get to these kind of bonding-like situations. Right? So that C1 phi 1 C2 phi 2 could look like something like a bonding situation between two nuclei. It could also look like something more complicated with multiple nuclei, multiple electrons. But this would be our starting spot. And I'm essentially going to say, when I extrapolate this out, I'm going to end up with looking at the bottom first. Again, I'm going to look at the bottom first. I'm going to end up with a bunch of integrals. I'm going to end up with a C1 squared integral phi 1 star phi d tau. I'm going to end up with a C2 squared integral phi 2 star phi d tau. I'm going to end up with a C1 C2 and a C2 C1, which is really just going to be 2 C1 C2 integral phi 1 star phi 2 d tau. And the reason I can do this is if I'm guessing real functions, then the phi 1, phi 2, that order can switch. If I'm guessing real functions, I can kind of switch which that is. I can get C1, C2, C2, C1. That's going to be the same thing. And actually, we could write them out. Let's write them both out just for a moment. If you already have your notes the other way, we can do C1, C2 integral phi 1 star phi 2 d tau plus C2, C1 integral phi 2 star phi 1 d tau. We're going to find that almost always we're going to have situations where we can add these together and get what I had before. But I decided I wanted to do this as generically as possible. We're going to define this integral. We're just going to call it something. Can we solve that integral? If it's a bunch of Gaussian functions, of course we can. So I'm going to define that integral as just integral S11. This is going to be integral S22. Can we solve that integral? Of course. If I told you what phi's we were guessing, we could use our integral tables and go through that. S12, S21. So our bottom in this rewritten way is going to be C1 squared integral S11 plus C2 squared integral S22 plus C1 C2 integral S12 plus C2 C1 integral S21. Where I'm leaving, and this is the thing that I really love about quantum mechanics, and I know it's not necessarily the best thing to love about quantum mechanics. When we get to this kind of symbolic level, we're just like, yes, we can solve integrals. Let's not worry about solving the integrals. Let's just do it symbolically and say those are integrals to be evaluated later. It's fun. It's fun. We do the same thing with the top. So when we look at this top part here, we end up doing the same thing. I'm going to have a C1. It's going to be a little bit more complicated. I'm going to have a C1 squared integral phi 1 star h hat phi 1 d tau plus a C2 squared integral phi 2 h hat phi 2 star h hat phi 2 d tau plus C1 C2 integral. In this case, it actually no, it doesn't. As long as we're Hermitian, we'll be okay here. phi 1 star h hat phi 1 e tau, and then I've got to fit one more in there, C21 integral phi 2 star h hat. Oh, I messed up. That should be a phi 2. Phi 2, phi 1. e tau. So this term should be a phi 1, phi 2. This one should be a phi 2, phi 1. We call this integral h11. So we'll do it later. We call this integral h22. This one h12. This one h21. So we get something that looks really similar to what we had before. We've got a bunch of unsolved integrals just hidden in there symbolically. h11 plus c2 squared h22 plus c1 c2 h12 plus c2 c1 h21. We've got our top and we've got our bottom, and because of the way we parameterized our problem, and the reason we can do this kind of simplification where we're just kind of ignoring the integrals for now, is because the way we parameterized the problem, picking it to be coefficients outside of functions, our Hamiltonians, all of our integrals are independent of the parameterization. Kind of a good choice. Because we picked it so our parameters were outside of the functions, we've created a set of integrals that are independent of our parameters. And that's going to be what allows us to simplify this down to a system of two equations and two unknowns. 5 more minutes and then we'll do the worksheet, because this next part, let's see. Can I get all? Let's see. Can I get all the way? Okay. Yeah. Okay. We can do this. So, E phi is going to be equal to, and there's two different ways to set this up. I think I might set it up the way where I think the derivatives are easier, because we could set this up as a parameter, as a fraction, where we have to do the quotient rule for derivatives, or we can multiply the bottom over and then take the derivative and apply the chain rule. I find the chain rule easier than the quotient rule. That's just me. But for that reason, I'm going to go ahead. If you remember, we've got this situation where I've got my E phi is equal to the integral phi h phi divided by the integral phi phi. I'm going to bring this part, which was all the S1s and S2s, over to the E phi part. So I'm going to have my average energy is going to be C1 squared S11 plus C2 squared S22 plus C1 C2 S12 plus C2 C1 S. Whoa, that's not what I wrote. S21. It's weird when I say one thing and my pen does another. I wonder how many times that's happened in my typos. I'm like, I'm saying, I got it. I'll have to go back and watch the videos. And this is all equal to, we're not done yet, C1 squared H11 plus C2 squared H22 plus C1 C2 H12 plus C2 C1 H21. Now, we've got two parameters. So we're going to have to do this twice. We're going to do d by dc1 of all of that, and we're going to do d by dc2 of that equation. And the reason I like setting it up this way is because When I apply the chain rule to the top here, I'm going to do the derivative of the first times the second. So I'm going to get dE phi. So if I do this, so let's do this. I'll do the C1 part, and then you've got to stop me. Otherwise, I'm just going to keep going. You got to stop me because I really like variation parameters, by the way. So if I do this first part, I'm going to do chain rule. I'm going to have d by dC1 of E phi times that whole thing. And the reason I'm not going to worry about this is because if we're defining the minimum, this term's going to set equal to 0. If we're defining the minimum, I'm going to set that term equal to 0, and then I'm just going to care about the second part, which is going to be E phi, derivative of the first times the second, plus derivative of the second with respect to C1. It's going to give me 2C1 S11 plus C1 S, whoa, got to take the derivative correctly. Derivative with respect to C1, I'm going to get a 2C1 there. I'm going to get a C2 S12 here, C2 S12, and then I'm going to get another C2 S21. Just taking the derivative, applying the chain rule. And then I'm going to take the derivative of the second half, because I've got to take the derivative of the whole thing. So I'm going to have 2C1 H11. This term, when I take derivative with respect to C1, goes to 0, because there's no C1 dependence. And then I'm going to get C2 H12 plus C2 H21. And essentially what we've started to do here is we've gotten to this point where we can start to recognize the fact that we've got two equations, two unknowns, or we've got one equation with two unknowns. And we can start to kind of collect the C1s together and see which parts go together. So like I've got my C1 S11, I've got my C1 H11, I've got my C2 H12s, and I've got my C2s here. I'm going to do the same thing for the C2 term. And then we're going to set it up as two equations, two unknowns. Yeah.
Wait, so what did you do between the first and the second one? So you did the chain rule in the first one?
So I did the chain rule in the first run to do the left-hand side of the equation. And then I just took the derivative of the right-hand side of the equation. So I took the derivative of this whole thing, that whole equation, both sides. We'll get to this next time. We'll get to this next time, but that's what we're going to end up setting up for our two equations, two unknowns. If you've never solved a series of equations using matrix mathematics, 1 through 5, solving a series of equations with matrices. Oh, it's so good. If you've ever gone online to balance a chemical equation, it's doing it with matrices. It's diagonalizing a matrix to balance your chemical equations. You can think of balancing a chemical equation as an n by n matrix system. And if you diagonalize it, you balance your equation. So we're going to look at, we'll finish setting this up next time, and then we'll look at how we use that to get some reasonable answers and start talking about the simple ideas of bonding. Any questions before I stop the video? Okay.